You got it? Thanks. I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. I thank you for these students again. I just pray that you'd help us to enjoy the break, which is about to start. And I just pray that we'd use this time wisely, Lord, to glorify you and what we do in this time. You know my prayer, Lord Jesus. Amen. Let me just talk about this for just a minute or two, and then I'll take your homework questions again. Or I'll do some homework, depending on which makes more sense. This is the so-called mean value theorem, right? It's on section 16.3 of Salas and Hilly. It states that if f is differentiable at each point on some line segment, then there's some point on the line segment such that the value of the gradient at the line segment dotted with b minus a is equal to the difference of f of b minus f of a. Now, if we knew this theorem, that homework problem that we worked out last class is utterly trivial, right? Because in the homework problem, you're given basically f of b is equal to f of a. So if you could use this theorem, that homework problem becomes immediate, right? And in fact, the proof of this theorem, since we already know the chain rule, is kind of silly, right? Like the proof is what? Consider g of t, which is equal to f of a plus t times b minus a for 0 less than or equal to t less than or equal to 1. Observe g is continuous on the closed interval from 0 to 1 and differentiable on the open interval to 0 to 1, as is clear from the formula. I'm assuming we know the chain rule, right? Hence, there exists, let's say, t sub c in the interval from 0 to 1 such that what? Such that g prime of t of c is equal to g of 1 minus g of 0 by the mean value theorem of single-variate calculus, all right? But we proved the chain rule, right? Independent of this, I mean, he uses this to prove the chain rule in Salas and Hilly, but I gave you an alternative proof, which was probably not totally rigorous, but whatever. Most of you don't care. So, sorry. G prime of t. I mean, I think if I ask the question in here, should I do more proofs or less, I'm pretty sure I know what the answer I get would be. Let's see here. Plus t times b minus a. I have a suspicion. So how do you differentiate that? Well, we're differentiating a function of a function, right? We need chain rule. And the chain rule we worked out here was that was the gradient of f evaluated at a plus t times b minus a, dotted with the derivative of the inside function, but the derivative of the inside function is just b minus a here. So when we come back up to the result of the mean value theorem, what pops out? So g prime of t of c is equal to the gradient of f at, some point c dotted with b minus a, but also g of 1 minus g of 0 is equal to, let's see here, f of b minus f of a. So these things matching up and identify c is equal to a plus t sub c times b minus a. That's clearly an element of the line segment from a to b. And there you go. That's a proof of the mean value theorem, assuming the chain rule. You'd say this looks an awful like the homework problem. You're right. We essentially proved this theorem in the homework problem I did the last class. That's why I'm going through it a little bit faster right now. Anyway, this theorem has its uses. It's good to be aware of it. Let me show you one of its uses. This is a standard result of multivariate calculus you should be aware of. It's important. Here's a little theorem. If the gradient of f is equal to 0 on a connected subset of Rn, then f of, whatever, x1, xn is equal to a constant for each, x1 in the subset. Whatever. I need to give the subset a name, do some name calling here. I'm going to call the subset U, okay? How do you prove that? So here's a picture, whatever. Here's U. So what you do, I'm claiming it's constant, right? So take any 2 points you like, so here's a point P, here's another point Q. If it's connected, what does that mean you can do? I can connect the points by some sort of broken polygonal path. I can take line segments, join them together, right? This is the meaning of the word connected. Essentially, it's the same as, for us, it's path connected. You can find a path from one point to the other, right? And we can just use little line segments to be boring. And then what can I do if I say that this is, let me call this, let me say P is equal to A1. I don't know, let me just keep it P. I need some labels for these intermediate points. What do you want? R, S, how about that? So what can we say about P, and what can we say about f of P minus f of R is equal to what? The gradient of f at some point C1 dotted with what? P minus R, right? Oh, I'm sorry, I should do R minus P. I'm an idiot. R and P, because, P is the starting point, right? And where is C1? Well, C1 it's somewhere in here, right? And how do I know such a point exists? The mean value theorem, right? Then what's next? F of S minus f of R is the gradient of f at C2 dotted with what? S minus R, right? And where C2 is some point in here. And what am I doing? How am I getting that? Mean value theorem, right? Mean value theorem applied to each line segment. One more application of the mean value theorem. We have f of Q minus f of S is equal to the gradient of f at some point C3 dotted with Q minus S, again by the mean value theorem, also known as Theorem 16.3 in section Theorem 16.3.1 on page 805 of Salas and Hilly. So then what? What are we given? What's that? But what are we given about this? So we're assuming that's 0, right? Yeah, add them up. So those are assumed to be 0. So yes, if we add these three relations, what do we get? We get f of P is equal to, sorry, let me add them actually. So what happens when you add? See what happens? The R's cancel and the S's cancel, and what are you left with? F of Q minus f of P is equal to 0. Therefore, f of Q is equal to f of P. Add 1, 2, and 3 to obtain this, okay? Now, I just did it for 3 points, but you can see this argument easily extends to finitely many points, right? And in a connected set, you can always join 2 points by, you know, a finite number of line segments linked together like this. And there you have it. The function has to be constant.
We're still kind of connected if if there's a spot where your subset necks down to a single point.
Yeah, because you could still pass a line through that point. So even if this had happened, as long as that point is in there, it's still connected because you can run line segments through there. Right. Now, if I remove that point, then all bets are off. Then the gradient of f being 0 on all this thing wouldn't say it's constant. It would say that it's constant on this piece and it's constant on that piece. So, of course, you can turn this around, right? If you study functions whose gradients are identically 0, and you see that, you know, the gradient being 0 allows for functions that have 2 different constants, then you know that your space is disconnected. But anyway. All right, well, I think I've got section 16.3 out of my system. There's more. I mean, this also, what's the next thing from this is if the gradient of f is equal to the gradient of g on a connected set. What's that say? That says that the gradient of f minus g is equal to 0 on connected set, right?
And the reverse.
That's also true, yeah. But what's this say then? This says that f minus g is equal to a constant, or in other words, f is just equal to g plus some constant. So gradients are always ambiguous up to a constant. You can always add a constant and still have the same gradient. Physically speaking, this is the freedom you have to adjust the potential energy to be 0 wherever you like. Well, that's not quite accurate. Well, I'll shut up. So you guys have questions? If you're fresh out of questions, I got plenty I can solve in here in the book. So, yes, go ahead.
Something like 56A.
Yeah, sure. So 56A would be something like, given g of r theta is equal to cosine of theta squared plus r theta, find the gradient of g in polar frame technology. So we took a lecture and we derived a certain beast. The beast we derived was this. The gradient of g is equal to r hat partial g partial r plus theta hat 1 over r partial g partial theta. So you just plug the formula you got into that thing and see where it takes you. What's partial g partial r? Theta, yeah. And what's partial g partial theta? Well, looks like minus 2 theta sine theta squared plus r. And there you'd have it. So that one's not bad, as long as you know the main result, which is that the gradient in the polar coordinate frame is r hat times partial derivative with respect to r of the function plus theta hat divided by r times the theta derivative of the function. With that result in hand, that's not hard. Is that seem reasonable for part A? Yeah.
For 57, B, when you square R before you find the gradient, or afterwards?
Yeah, you can do it either way. You can either do straight computation of this, or you can do that the gradient of r squared is equal to 2r gradient of r. That is a chain rule, which is true for the gradient.
All right.
No, it gives you the same answer. I'm not sure which is easier.
Might be a silly question.
I can only hope.
Okay. Problem 53.
Uh-huh.
You just add the two equations together to eliminate dw?
Yes.
Okay.
Yeah, if you add the equations, it gives you 2dz. Yeah, I would strongly advocate adding and subtracting those equations as a method to select the either dz or dw differential from the equations. Absolutely, adding and subtracting equations is the way to go there.
And your answer won't necessarily use x, y, and w, right? It says you can use those, but will it necessarily?
Oh, I don't know.
Okay.
It doesn't have to. There's a lot of ambiguity possible in such questions because we have these relations between the... Are you talking about 53?
Yeah.
Oh, see, 53 is kind of funny because you don't actually have formulas for z and w, right? You just know they're differentials. So, yeah.
60. How do we know that we found the 6 equations? What do they look like? I mean, what sort of conditions are they? Something like df has to be 0 or something more specific?
Well, let's think about that. So the question is something like you've got f of t, x, y, and z, and supposedly it's going to be the gradient. Oh, I'm sorry. The gradient of this, is it I use a big F for the memory. And that's going to be a vector field. What are my letters for it? PQRS. PQRS. And the question is, what conditions on P, Q, R, and S are necessary so that you know that such a potential function can exist, right? So just go back to what did we do in the two-dimensional case? Right, but just think about the basic logic of it to start with. It was, we had what? We had partial f, partial x is equal to p, and we had partial f, partial y is equal to q, right? And what was the combining, the linking condition was that fxy is equal to fyx, right? Which gave us the condition that, py is equal to qx ultimately. So here what do I have? I have fx is equal to p, I have f sub y is equal to q, I have f sub z is equal to r, I have f sub oopsie, try that again. Try that again. The first variable is what? T, so I should t, x, y, z, right? So what do you know? I mean, you know the partial derivatives commute. So f of tx should be equal to f of xt, right? Or if I write it more operationally, this is f sub t taking the x derivative is equal to f sub x taking the t derivative. But what is that? I mean, this is really not necessary. You can just look at that if you want. Yes.
So we have to show
Hmm? So you've got t with x, t with y, t with z, x with y, x with z, and f y with z. 1, 2, 3, 4, 5, 6, yeah.
lay them out in 6.
All possible distinct second partial derivatives have to commute. Now for 3, if you just have if you have a 3-dimensional vector field, then you just have 3 conditions, right? You have to have the xy derivatives commute, the xz derivatives commute, and the yz derivatives commute. So you end up with 3 conditions in 3 dimensions for this exactness. The vector, I mean, you could say the vector field is exact. I mean, I guess we say it's conservative more often, but I mean, I guess you could call it an exact vector field. That wouldn't be such an abusive language. Here, let me work some more problems from the book, unless you guys have another question. Do you have anyone have a pressing question? Go for it.
Just for 55, like I'm kind of confused on the partial z partial y, like that whole chunk, like there's not another equation where that's coming from.
You have x squared plus 3xy plus z cubed equals to 10. Right? So let's see here. How would I find partial, where was I? Partial z, partial y. What I would want to do, I mean, there's 2 approaches. The one is I can just if I say partial z, partial y, what am I doing? I'm holding x fixed, right? By process of elimination. It has to be that. So the one way I could do it would be simply method differentials. Take the differential of this. 2x dx plus 3yz dx plus 3xz dy plus 3xy dz plus 3z squared dz equals to 0. So that gives me dz is equal to, what are my dx's? One here, one here. So I get 2x plus 3yz dx. What's my y's? 3. Oh, excuse me. 3xz. Anything else? That's it, right, for the y's? All divided by, what are my dz terms? I got this one, and I got this one. I got to bring them to the other side, so I get minus 3xy minus 3z squared. So with that, I can read off that partial z, partial y holding x fixed is 3xz divided by minus 3xy minus 3z squared. If I haven't made a mistake. Yeah?
How did you get from the second to the last line to the last line?
Going from here to here?
Yeah.
Well, remember, what's going to happen by the method of differentials is you have partial z, partial x, holding y fixed, dx, plus partial z, partial y, holding x fixed, dy. So all I have to do is to compare the coefficient of dx to get that. But of course, I wanted the y derivative, right? So I compared this other piece, right? What's the other way I could do this calculation? Ah, you're like use the result, that partial, very good. That's another way. That's the third way. I wasn't even thinking of that. You're like partial y, partial holding x fixed. I could do, that's really f minus f sub x over f sub y, right? Or f sub z? F sub z, where you're saying that this whole thing is f. That is another way you could do this. That would be also correct. These terms here are precisely what I have. Like this is f sub x. This is minus f sub z. It's exactly the same thing. I was thinking a little bit more low-tech, though. You could just differentiate this with respect to y holding x fixed. So this approach is sort of the least theorem-based. The only thing I remember for the approach I'm writing in blue at the top is that if I hold y fixed, if I hold x fixed while I'm differentiating with respect to y, that simply means that partial x, partial y, and partial y, partial x are 0. They're independent, right? In particular, partial x, partial y is 0. So as I do this differentiation, that's gone. And this just gives me 3xz. And then what? Oh, I'm trying to count, but z is a dependent variable is the thing, though, right? So I get 3xz plus 3xy partial z partial y holding x fixed by the chain rule. See, because this is a product of, y and 3xz. The point is z is a function of y here. So I have to do the product rule on that middle term. And also, that term gives me plus 3z squared partial z partial y holding x fixed. And all of that's equal to what? 0, right? So what's that tell me? Partial z, partial y holding x fixed is equal to what? You solve for this. You get minus 3xz divided by 3xy plus 3z squared. I think I dropped, no, I didn't. Oh yeah, what do you know?
Just have the negative in the
Of course, you know that works out to minus 1 from the general identity we did the other day with the PV equals nRT, remember? We proved that for arbitrary functions of 3 variables, that particular product of partial derivatives must work out to minus 1. I want you to do it for that particular function because that gives you a nice chance to do 3 derivatives and make sure that they're all right. The showing that their product is minus 1 kind of gives you a consistency check on those 3 derivatives that you're calculating, right? Does that help or? Yep.
Can you address the questions at the end of this puzzle, like when it's asking about the implicit function or doing it locally?
So the question is, explain where the implicit function theorem allows us to view z locally as the graph of a function in x and y. Right? So the answer is that that's going to be true wherever f sub z is not equal to 0. So generically speaking, right, folks, you've got fx dx plus fy dy plus fz dz equal to 0. So essentially, if if you can solve for dz meaningfully, then, well, anyway, the theorem is that if f sub z is not equal to 0, then locally can find h of x comma y such that f of x comma y comma h of x y equals to a constant. So you're just looking for where the z derivative is non-zero. And the place I talk about that, I think I talked about that before. I may or may not have. I should have talked about that for like the sphere. If you think about solving for z as a function of x and y for the sphere, that's the easiest example to illustrate this theorem on. Right? So here that's the f, right? So f sub z is what? It's 2z. So I can solve z for a function of x and y locally on some open set around any solution, any point on the sphere, except for the points with z equal to 0. I can't say anything from the theorem there. It may or may not be possible to find a function to write the sphere as a graph at those points. In fact, it's not, because you know the sphere, unfortunately, on the equator, right, which is where z is equal to 0, you fail the vertical line test. If you tried to use a graph, if you tried to use a graph built on the sphere like there, if you take a vertical line and you pass it through you'll hit 2 points, right? So it would fail the vertical. It can't be written as a graph on an open set around the equator. You could go like above the equator or below the equator, but those wouldn't be open sets, and that's why the implicit function theorem breaks down there. Basically, it's where you get the plus and the minus square root in the algebra joining at the equator, right? On the top, you've got the square root of 1 minus x squared minus y squared equals to z. And on the bottom, you've got z is equal to minus the square root of 1 minus x squared minus y squared. And that's the significance. When the z derivative is 0, it shows you probably that's where you're going between different cases in your possible solutions. But anyway, that's kind of a challenge comment in the homework. It's not something we've really covered in depth in here, right? That's an advanced calculus. To really get into what I'm saying is advanced calculus. It's not here. Yep.
On problem 51, when it says at points C naturally,
Well, you could talk about the normal to S2 any place on S2, right? But I'm interested in how the normal to S2 behaves along the curve of intersection. Right?
So the word naturally can be admitted there without changing the meaning of the problem.
Yes. You say you could cross out the word naturally and it wouldn't change the meaning of the problem. Yeah. That is a helpful comment, Luke. Thank you. So what you guys are telling me is my use of the word naturally is unnatural. I'll accept it. Other questions? Let me work some problems from 19.2. It'll probably be helpful for you guys in the big scheme of things. Did you have a question, Mike?
I did, but I have no idea what it was.
Uh-oh. Well, hey, maybe this is the question. The one I'm about to work, maybe this is the one. It could be, So I gave you guys a handout, which is kind of silly because it's actually section 19.2 in your book. I forgot about that. For some reason, they stuck the exact differential equations all the way back over here just to make life difficult for us. So here's section 19.2, numero uno. We've got x, y squared minus y. All right, I'm going to change the problem. This is dx plus x squared y minus x dy equals to 0. That's essentially the problem which is given. And the question is, to find the maximal simply connected region on which the equation is exact. And in each of these cases, there is one such region, and find the integral curves. In the language I was using the other day, we would like to solve this differential equation if it's an exact equation, all right? I think this will be exact from the language here. Yeah. All right, so how do we solve this differential equation? What did we say? We want to think of this as being, we call this omega for just a second. And so the idea is that omega is actually equal to df for some function f. And so that implies that f of x comma y equals to a constant is the solution to the differential equation. All right, that's the overall theoretical backdrop here. That's what we proved the other day. I don't want to prove it again. All right, that's what we're going to use. So, can you find such an f? What will we need? We need this is partial f partial x, right? And we'd want partial f partial y is equal to what? So let's see here. There's a couple different ways to attack these. I'll do it the boring way. Integrate this holding y fixed. If we do that, what do we get? One half x squared y squared, right? Minus xy plus c1, which could be a function of what? Y. Y is fixed. Y is the constant here. So I integrated with respect to x, right? So, I mean, you could think of this as being an integral over partial x in some sense. Step one. Step two, plug that in to this. So step two, I plug in into that and see what happens. So if I take the y derivative of that, what do I get? I get x squared y minus x plus dc1 dy is equal to x squared y minus x. If the equation is actually exact, when you do this, it will work out. If it's not exact and you try to do this, it will blow up in your face and we'll get a nonsensical equation, right? A quick check, though. If this is m and this is n, you can check that partial m partial y is equal to partial n partial x, right? What's the y derivative of this? It's 2xy minus 1. What's the x derivative of this? It's 2xy minus 1. See? They match. It's exact by that test. But then that doesn't tell me what the solution is yet. So these cancel. What are we left with? We're left with dc1 dy equals to 0. So therefore, I can take c1 equals to 0 is a solution. Okay, so fine. In short, the solution then is f of xy. The integral curves of this differential equation are 1/2 x squared y squared minus xy equals to some constant. And there you have it. Different values of the constant give you different curves. Each one of those curves solves the given differential equation. On what simply connected domain? Where can you do this for? As far as I can tell, this is good for the whole plane. Doesn't look like there's any obstruction to what we're doing at all. So I think the maximally connected, maximal simply connected region on which you can do this is the plane. Number 5 is the next question that I recommended you to try. Let's look at that one. Here we've got natural log of y plus 2xy times dx plus x over y plus x squared dy equal to 0. All right, well, I mean, already when they write this, what can you tell me about the region that we are considering? Y is greater than 0, right? So automatically, this differential equation is only defined on the upper half plane. And y equal to 0 is hard to do here. So that's out. So the original differential equation automatically already tells me that the upper half plane and the x-axis are out. Okay, so same song and dance. This is going to be partial f, partial x. This is going to be partial f, partial y. I think that we should try partial f, partial y first. Integrate this with respect to y. What do we get? We get minus x over y squared. Oh, wait a minute. Excuse me, what do we get? What's the integral of 1 over y? X ln of y, right? Now, we're going to assume that y is greater than 0 throughout the rest of this problem. That's why I don't have to put the absolute value of y here. And then plus what? Plus x squared y. And sorry, what's the integral? What's the integral of partial f, partial y with respect to y? It's f again, right? So f is equal to x ln of y plus x squared y plus c1 of what? Now this time it's of x, right? Because in the first time I did the x integration. This time I'm doing a y integration just to be different. Now plug this result we just found, plug star. Partial f, partial x equal to what? Natural log of y plus 2xy. So if you do that, what do you get? Natural log of y plus 2xy plus dc1 dx is equal to natural log of y plus 2xy. All right, so it worked, right? And we just say that C1 equal to a constant, right? You can let the constant be 0 since we're going to use, I mean, you could pick the constant to be 3 or 7, whatever you want. It doesn't really matter. So the solution is what? F of xy. We have x ln of y plus x squared y equals to a constant. Those right there, the locus of points in the plane, upper half plane, which solve that equation are the integral curves to the given differential equation. We're always using this little thing up here. If omega is equal to the exact differential, if omega is equal to df, that implies that f equal to a constant is the solution, right? I mean, if you'll allow me this, if you have omega is equal to df, right, is equal to 0, then d omega is equal to d squared f, which is equal to 0. I guess it doesn't help you guys any. Let me make it go away. It's not helping you guys. Let me make that go away. It never happened. Strike it from the record. Let's see here. Is there another one we should do? How about number 27 in the same section 19.2? For what values of k is the following equation everywhere exact? I'm going to go ahead and do part B because that one looks more fun. So here we have y e to the 2xy plus 2x parentheses dx plus parentheses kx e to the 2xy minus 2y dy. Oh, sorry. So how would you see where it's exact? What could you? We have that theorem we could check, right? What was the condition we need for exactness? Remember our little theorem? If this thing is m and this thing is n, then we say that it's exact. It is exact on simply connected domain if partial m partial y is equal to partial n partial x. Now, this simply connected domain stuff, don't worry too much about right now. This calculation is going to make sense on the plane. The whole plane is simply connected. So, you know, whether or not you have a technical understanding of what simply connected means just yet, it doesn't hurt you. So we just used that little theorem. And remember what that was? That was that the partial derivatives commute, right? So what do we have to have? Partial m partial y is what? Product rule, right? So I get e to the 2xy plus 2xy e to the 2xy, I believe. Do you guys agree? Do you disagree? What do you think? Okay. Partial n partial x partial x of kx e to the 2xy minus 2y, what do we get? Well, I think we get k e to the 2xy plus 2kxy e to the 2xy. Let me check on that. Yeah. So if we set these equal, what happens? K has to be 1. Now, how did you see that? Just guesstimating? Now let me see if I can believe you. First of all, I'm going to divide the equation by the exponential. Why is that safe? Yes, exponential is never 0, which means dividing by it is a safe move. So if I divide by the exponential, I'm left with the equation 1 plus 2xy is equal to k plus 2kxy. Now, this has to be true. This equation is true for all values of x and y. So here's how we can get to what you guys just pulled from the thin air. If you put x equals to 0 and you put y is equal to 0, what's that tell us? 1 equals k, right? Now, if I take this thing, and if I call it Pac-Man, and if I take the partial derivative with respect to x and then the partial derivative with respect to y of Pac-Man, what do I get? I get 2 is equal to 2k. So therefore, k is equal to 1 again. I don't know. I mean, well, okay, there's something I would like to say that I can't say yet because we haven't done a certain thing. But yes, you guys are right. K is equal to 1. That's the solution. It's kind of an interesting little bit of algebra anyway there. Yeah. Other questions? I wanted to do a few more of these because I wanted you to see that if you didn't understand it the other day, you really should understand how to do these 19.2 problems. I will ask about one of these on the test, all right? Not one of these, exactly one of these necessarily, right? But this kind of problem. This is an important calculational technique that you need to learn in this course for your own edification as a student of the math. How about this? But you see, if I go back to section 16.9 and I start doing these problems, you're going to feel like I'm doing the same problem again. Right? 16.9. Let's say number 7. Here you're given the vector field cosine x, cosine x minus y sine x, comma, cosine x. And the question is this vector function a gradient? In other words, does there exist a function little f such that the gradient of little f is equal to the given vector field p comma q? I've deliberately used m and n for the differential equation and p and q for the vector field to try to distinguish the concepts in your mind. But you see, really, the role of p and q and the role of m and n are much the same. Right? So to see if this is possible, what do we have to do? We have to solve cosine x minus y sine x is equal to partial f partial x if we can. And cosine x is partial f partial y. Can we do it? I don't know, maybe. This says that f is equal to what? C1 of what? What kind of constant? What did I do? I integrated this with respect to what? With respect to y, holding x fixed, so that means x is like a constant, so C1 could be a function of x here, right? Now what do? Try plug it into, plug star into the other one, partial f partial x is equal to cosine of x minus y sine x. Let's see how it goes. What happens? Well, differentiate this with respect to x, I get minus y sine x plus dc1 dx is equal to what? Cosine of x minus y. Hey, this one's more exciting than the ones we've done so far today because the c1 doesn't be a the constant's not a constant actually. It's actually a function for this example. I'm happy. This is finally interesting. That's gone. And so what is c1? Sine x, right? Integrate. C1 is sine x. And so there you have it. The potential for this vector field is in fact y cosine x plus sine x. The gradient of this function gives you back the vector field. Yeah.
How did you get the cosine x minus y sine x equals partial f partial x?
So this has to match that, and this has to match that if it's going to be the gradient.
Sorry, I was looking at the I get it.
Where's the differential equation? I don't know. That's not this problem, right? But it's the same math. You see that? Like if I was to write down the differential equation, cosine of x minus y sine x dx, right, plus cosine of x times dy equals to 0, and I was to say solve it, you should immediately be able to go y cosine of x plus sine of x equals to a constant is the solution. Done. Given this, of course.
So you can just like pick randomly, basically, whether you want to integrate partial fraction.
Yeah, there's a subclass of malevolent examples that if you choose wrongly, you'll actually have to do an integration. Whereas if you choose wisely, you don't really have to do an integration. Like, there are examples where if you differentiate with respect to x, it's integration by parts. But if you differentiate by y, it's just like polynomial integration. Let's see if I can find one of those in here. Yeah, maybe this one. Watch it be one that's not exact. Y e to the x times 1 plus x this one I didn't recommend, so who knows what's going to happen here. X e to the x minus e to the minus y. So the question is it possible to write this as the gradient of a function? I'm not even going to check the theorem to see if it's possible. I'm just going to go into the y. I'm just going to just go into it like a bull in a china shop, just see what happens. Is that an expression people know anymore? I don't know. It's an expression. All right, partial f, partial y. Now you see why partial f, partial x is nasty. I mean, it's not super nasty, but I'd actually have to integrate by parts on that if I did this x integration first. But on the flip side, if you look at partial f, partial y, See, so given the choice of which one of these to integrate, the choice to me is clear. I integrate the second one, because this one actually requires thinking. We don't do that. So f is equal to x, y, e to the x, plus e to the minus y, plus c1 of what? Of x. And then you differentiate this, right? With respect to x. And when I do that, I get myself a y e to the x plus x y e to the x plus dc1 dx equals to, apparently, y e to the x plus yx e to the x. See, something wonderful has happened. We never had to integrate by parts. These cancel. These cancel. We get c1 is equal to a constant. And so in fact, the function, the potential function for this vector field, f of x, y, is x, y, e to the x plus e to the minus y. There you go. That is, in fact, the potential function. I never had to integrate by parts. Woohoo! See if I had. And there are other. It can get worse. It could be an integral of natural log. It could be a trig substitution. I mean, there is. In fact, there will be problems later in this course where flipping the order of integration makes a problem possible that wouldn't otherwise be possible. We'll see this. There's these kinds of freedoms sometimes have to be exercised. Otherwise, you'll be stuck. Problem 19 is probably like that. Well, yeah, let me see if I have time. Are there any other questions about other problems, though, before I do another one of these? I think it's good for you guys to see a bunch of these. So it's even better for you to work a bunch of